Yeah, comes on everyone. The cloud storage has become full. Had to delete it. Anyways, so the last thing we did was bulbs. Next thing, there's a small concept called fuse. So what's a fuse? It's a safety device. So let's say something happened in the house and there's a short circuit. So a large current flows through the circuit and this thing literally damages everything. So you want some kind of a safety mechanism. Nowadays, so we have this kind of switches you can see in the house. They just strip. You just have to go and put it back. So let's see. So this thing, if you actually look at it, if you ever bought a, this thing, what do we call this? The extension box, the power supply thing, you'll sometimes notice this. They'll give you a small glass thing like this, like a fuse. Ever seen something like this? So it'll be like a small cylinder there. So this wire inside here is the fuse wire. So these things, right, have a certain rating. Like, do one thing. Next time, observe, when you switch on your AC का switch के ऊपर देखो, it will be written some 16 ampere. Ever seen that? On top of your switch, it will be written some number. So it'll be a little there. So what this means is, these things can carry only a certain current. Once the current exceeds this wire will melt and the circuit gets disconnected. Like I said, this is an old model. Nowadays, so we use semiconductors. So let's say if something written as 10 amperes, it means if I is greater than 10 amperes, the wire melts and circuit gets disconnected. So this fuse wire is made of material of low melting point because you want it to melt very fast and low specific heat capacity. You want the temperature to increase pretty fast and you want it to reach the melting point pretty fast because you want it to get disconnected when there's a large current. So when the current exceeds a certain value, I square R, the heat produced will raise the temperature. So that's about a fuse. Yeah, let's see our question based on this. So let's say we have a 10 ampere fuse, which is 10 ohms. This is a 5 ampere fuse with a resistance 5 ohms. And you're sending current I. So find the maximum I so that none of the fuse gets burned out. Okay. Hmm. So now see here, when you say maximum current, right? One thing is sure, one of the fuse is having a maximum current. So we just need to see this. Let's say this is I1, this is I2. We know both are in parallel. So I1 into 10 must be equal to I2 into 5. So we get 2I1 is I2. So this is the ratio of the currents. So first possibility, let's say if I1 is 10 ampere, then I2 would be 20 ampere. So this is wrong. Since you said maximum current, matlab one of the fuse is carrying maximum current. The second possibility, if let's say I2 is maximum, then I1 is carrying 2.5 ampere. This is acceptable. Therefore, 7.5 ampere is the maximum capacity of these. Clear? So when they're in parallel, still the concept of resistance still works. Have a look at this. All clear? Simple thing. That's the thing about fuse. Next thing. Instruments. Advanced में quite a good heavy weighted topic this is. Because this thing can come in electrical current electricity, or you can ask them as electrical instruments. Now, when you talk about instruments, technically speaking, right, there is actually only one instrument that we have. With that, we create everything else. So there's only one thing that we have, which is a galvanometer. More about the construction and its working, right, we will study in magnetism. But for now, we can see it's a current sensitive device. Where current flowing through it is proportional to angle deflected by the needle. How did you get the proportionality? How it works? That let's not get into it right now. That we will see in magnetism. So for now, we know this much. Whenever the current flows, this thing is going to deflect. So if you see a galvanometer, this thing has readings like 0 milliampere, 1 milliampere, 2 milliampere, 3 milliampere, again 2 milliampere. You can construct any type. So if the current is flowing this way, then the needle would deflect this way. If the current is flowing in the opposite direction, the needle will deflect in the other way around. So this is the symbol we use. But generally, right, we can manufacture one where goes from 0 to 10. So this thing is Rg. Rg is the resistance of galvanometer. This is Ig. So generally for a galvanometer, the biggest problem is the range. The range is in microampere to milliampere. It measures very small current. It cannot withstand. That is because, in order to make this very sensitive, we use very thin wires. And when you have such a thin wire, they have a large resistance and more current flows, they will burn out. So if you use thick wires, it won't be sensitive. So we have a problem. So this thing cannot measure large currents. It can measure only milliamperes to microampere. Your AC uses more than 10 amps. So we need to do something about that. Now, sometimes they use the word full scale deflection. Matlab, the scale is completely full, or it has moved all the needles. Needle has gone to the maximum. That means we are talking about maximum current IG. IG is the current in galvanometer. There. So this is the equipment that we have. Clear? Now, using this, we need to make a device which can measure larger currents, like 5 ampere, 10 ampere, 20 ampere. Any doubts on this page? Going ahead? Going ahead. So the first device we make is an ammeter. Main thing about this thing, right? As long as you remember how each thing is made, the questions you'll be able to handle. So it measures current and is constructed by shunting. Now, when you hear the word shunting, meaning keeping in parallel. If I say I'm shunting the battery with a resistance, meaning I kept a resistance in parallel with the battery. I'm shunting the battery with a capacitance, means I'm keeping a capacitor in parallel to the battery. I'm shunting a resistor with a capacitor, means I'm keeping a capacitor in parallel to the resistor. So shunting, the word means keeping in parallel. So by shunting a small resistance to the galvanometer. And let's see how that works. So first thing, ammeter should be placed in series. An ideal ammeter has zero resistance. So let's see the working. So you take a galvanometer and you take a shunt resistance. This is R shunt. This is RG. So capital I is going here. IG current will go in the galvanometer. So this full package here is what we call as an ammeter. So this whole setup here is your ammeter. Now look at this thing. Because they both are in parallel, we can clearly see the current here will be I minus IG, and that is IG. So IG into RG must be I minus IG into R shunt. If I rearrange the terms, I will get I is equal to IG into 1 plus RG by R shunt. This is your final result actually. So what this gives you is a relation between Ig and the capital I. I'll show you how this works in the next page. But understand one thing: the galvanometer, technically it measures Ig, but we want to see capital I. There's a difference. What you measure and what I see will be different. Because see, galvanometer ka needle will move because of which current? Ig, right? It doesn't know who is capital I. So whatever deflection you will get is because of Ig. And there is a relation between Ig and capital I. So we need to manipulate this galvanometer to show capital I. This is what we call as, calibration. Let me show you that in the next page. I think you should note down this formula here. We're going to use this. Put down that formula. But more importantly, understand how I derived this. The idea is more important how I derived it. Pretty simple derivation. When you shunted, both will be in parallel. So current will split. And from there, you can find the relation between capital I and Ig. Because my galvanometer can measure only Ig. It doesn't know who is capital I. So what we do here, tell me one thing, what does a weighing machine measure? What does it measure? For be more specific, it measures normal reaction. It doesn't know what is mass. It measures normal reaction. And then what does it do? It divides it by 9.8 and gives you the mass. So what it measures and what it shows are two different things. Example, if you look at your weighing machine, measures normal reaction. It doesn't know what is mass. What if you're standing on the weighing machine with a bag? Right? There can be more weight there. So what is measuring is N, but it shows N by G. So here also we're going to do something similar. So what we will do, here we know capital I is Ig into 1 plus Rg by R shunt. This entire term is the multiplying factor. Now, for example, let's say 1 plus Rg by R shunt. Now, see, this is in your control. You can put whatever value you want for shunt, and let's say I get this value as 1000. So what you did, your galvanometer, which is there, let's say this thing is showing 0 milliampere, 1 milliampere, 2 milliampere, 3 milliampere, and let's say 4 milliampere, and so on. This is your Ig. Now look at this thing. Because now the relation between capital I is 1000 times Ig. I will just erase all these symbols here and I will write 0 ampere, 1 ampere, 2 ampere, 3 ampere, and 4 ampere. Now, whenever the current flows in the wire and when the needle shows like this, so it is actually measuring Ig is 2 milliampere. But I know relation between Ig and capital is 2 ampere. So because now these symbols are not there, you're getting it? We will erase this blue symbols there, Ig ka. So even though it is measuring Ig, it is showing you capital I. Is that making sense what we did? We manipulated the galvanometer. See, it will always measure Ig. It doesn't know who is capital I. By you adjusting the values of that R shunt, right, I can make it show something else here. So if you see here, when Ig is 2 milliampere, capital I is 2 ampere. So the needle measures 2 milliampere but shows 2 ampere for us. They successfully have converted galvanometer into an ammeter. You can measure larger currents. For example, if this value is not 1000 but 500, then what will you see? Then you will see 0, 0.5 ampere, 1 ampere, 1.5 ampere, and so on. Are you getting? You can manipulate the multiplying factor and you can get different ranges there. Is this clear, everyone? How we used a galvanometer which measures in milliampere to measure amperes. This is what we call as calibration. We do this with the springs also. What does a spring balance measure? It measures tension in the spring. We make it show kgs in the weight. Any doubts on this thing? Please ask me. It's quite a important thing. You should know how it works. So you erase this blue color thing. Now, for you who have never seen before this, you don't know what is IG. You will only see capital ICA markings there. But inside you manipulated everything. Whenever it measures 2 milliampere, you made it to show 2 ampere. So we know the actual current which is flowing in the main circuit. Any doubts on this? Maulika, Swastika, clear with this? Vidyut, Yasha, Rehan, Ishan, clear?
Yes, sir.
Aditya, Anika, Adrit. Perfect. Now, while constructing this, we have to take certain precautions. First thing, R shunt must be very small. Why? First reason, range increases. You can measure larger currents. Because if you see capital I is Ig into 1 plus Rg by R shunt. So if the shunt is small, you'll get a bigger multiplying factor. Second, if R shunt is small, then max current flows through it. Because when you're in parallel, smaller the distance, more current will flow. And because of that, and Ig becomes small. And that is good for me. I don't want big Ig. Because if the Ig, that is the current in the galvanometer, exceeds certain value, right, it starts burning out. So galvanometer is protected. Third, error decreases. So let's say if you have a battery and a resistance, technically speaking, the current I should be V by R. Now, because you wanted to measure this, you went and brought an ammeter and kept it in series. Now, the problem is, because you kept an ammeter, you yourself messed up the whole reading now. Now, the new current I dash will be V by RA plus R. So, the very act of observing this current messes up the reading. And we know 1 by RA, it is parallel 1 by RG plus 1 by R shunt. So, if R shunt is small, RA is small, so error becomes less. So you can't avoid that error by introducing an ammeter into the circuit. You messed up the whole reading. You created an error yourself. But at least by keeping R shunt small, you can make the whole ammetric resistance small, and therefore the error would decrease. At least you'll get closer to the actual value. Is that clear, everyone? So these are the three things. So the galvanometer here and the shunt here. You don't want too much current in this IG. You want maximum current to flow through this shunt resistance. So it gives you more range, it gives you protection, and it gives you decreases the error. So keeping the shunt resistance small has its advantages. That is how an ammeter works. Clear, everyone? Next thing. Any doubts on this? Please ask me. So if you see, technically, there's only one formula there. Capitalize Ig into this. Next thing is a voltmeter. So voltmeter is, it measures voltage. And is constructed by keeping a large resistance in series to galvanometer. Like I said, end of the day, the only one who can deflect is galvanometer. We have to manipulate that guy only to give you everything. So this is how we construct. So first thing, voltmeter is kept in parallel. So whichever device you want to measure the potential difference has to be kept in parallel. Voltmeter is placed in parallel to the device. Don't get confused. Huh? To construct it, you have to keep a resistance in series. But to measure voltage, the voltmeter must be kept in parallel so that they get same voltage. An ideal voltmeter has infinite resistance. It behaves just like an open circuit. So this is how it works. So we have an external resistance. You want to measure the voltage across this. So we have a galvanometer and we keep, this is R large. This is R shunt. This is capital I and this is Ig. So here, this whole thing is a package. That's your voltmeter there. So pretty straightforward here. So the voltage across the R external will be how much? Now the voltmeter and this thing are in parallel. So whatever is the voltage across the voltmeter, that is the voltage across the R external. So that would be Ig into R, sorry, this is Rg. Ig into Rg plus R large. That's straightforward. So V is equal to Ig Rg plus R large. This is the formula, straightforward. So here the multiplying factor is Rg plus RL. So again, we do the same manipulation. So when you take this galvanometer, so let's say this is 0 milliampere, 1 milliampere, 2 milliampere. So you're actually measuring Ig. So example, let's say you can take Rg plus RL as 10,000. So now what you're showing, this will start showing voltage. This will become 0 volt. This will become 10 volt. This will become 20 volt. Are you getting it? So when the voltage across the device is 20 volts, Ig ka value will be 2 milliampere. So this thing is measuring milliampere current, but it is showing you voltage. So you can manipulate this thing to show voltage also. Have a look at this. Like I said, the working construction derivations are quite easy, straightforward. But you should know how these things are working. So now R large is in your hands. You can change whatever value you want. So the multiplying factor is adjustable. Like I said, the only device that you have which can deflect is the galvanometer. Somehow we have to use that to manipulate and create everything else. There, this thing is actually measuring Ig, but it is showing you voltage. Clear with this, everyone? Do have a look at this. Clear? Next thing. Some precautions. When you're measuring this, R large must be large. Why? First thing, range increases. Same reasons actually. Because the multiplying factor here is Ig into Rg plus R large. Second, if you put a large resistance, less current will flow through it. So Ig decreases. So protection. You don't want a big current in the galvanometer because it can measure only up to milliamps. Third, error decreases. Same reason. By introducing a voltmeter, you mess up the whole reading. But when you keep a large resistance in parallel, the overall resistance won't change much. So the same precautions you have for precautions, matlab the same things you have for shunt and this thing. There, that's about an ammeter and voltmeter. So there are simply straightly two formulas, that's it. But you should know how it works because we can manipulate a bit here and there. Any doubts on this? Okay, let's see a question. The best way is once you start questions, you'll get the hang of it. They're not tough, but you should know. Let's get them both. Yeah, first one is easy. First one कुछ ही नहीं था देखो. Since the current is splitting equally, both the resistance must be same. Isn't it? Straightforward. So I by 2 into 20 must be equal to I by 2 into Rg. So Rg is 20. Why will the current split equally? Because both the resistances are equal. What about B? Mhm. Let's see. B, okay. Try. I'll give you a minute, everyone. The galvanometer has 20 ohm resistance and reads full scale of 0.2. The meaning of this is when the current is maximum in the galvanometer, it will show 0.2 volts. Now you want to convert it into 10 ampere ammeter. The galvanometer should have. Full scale, matlab max IG. Then this 0.2 would be max voltage it can measure. Basically, the range of the voltmeter is 0.2 volts. Okay, I think most of it did get B. Try others. I'll give another 20-30 seconds. So indirectly it is saying IG is the voltage across by RG. So you are measuring 0.2 volts and RG is 20 ohms. So IG is 0.01 ampere. So the maximum current you can measure in the galvanometer is 0.01 ampere or 10 milliamperes. Anything more than this, the galvanometer will burn. So the first point, right, this is given only to find IG. Now you want to construct into a 10 ampere ammeter. Matlab you're saying capital I is 10 ampere. IG ka value I know. So I is equal to IG into 1 plus RG by R shunt. This is the formula we have to use. So capital I is 10, IG is 0.01. This is 1 and this is 20 by R shunt. That would be 20 by R shunt is approximately, that is 99. You can approximate it to 100. That would be 0.155 to 0.2 ohms. Did I miss out on something here?
1000 होगा ना
1000 होगा, yeah, 0.02 ohms. So B is the answer. And since you are constructing an ammeter, it should be in parallel. So shunt resistance, B is the answer. Easy. So the starting part, the first line is they gave you, if you just kept the galvanometer across a voltage, you'll get this much. So from there you can measure the IG ka value, and from there we can use this. Let's see one more. Get them, you got a minute. Okay, let's see. The first one. Now, if you want to measure Ohm's law, you're trying to use V is equal to IR and you want to get that ratio. So voltmeter must be in Voltmeter must be in parallel. Ammeter must be in series. So that's the main idea there. Voltmeter is in parallel to R and ammeter is series to R. Which one is that? B, no? That's your answer. What about D? A galvanometer may be converted into an ammeter or voltmeter. In which of the following cases, resistance of the device will be the largest? First thing, among ammeters and voltmeters who have a large resistance, voltmeter. And among the voltmeters, how do you get the range? We get the voltmeter ka range is Ig into Rg plus RL. So for more range, we need to keep more resistance. RL must be large. So among the devices, whoever has a more voltage range must have more resistance. Make sense? Between a 10 volt and 5 volt ammeter, voltmeter, the one with the larger resistance in series will have a larger range. Clear with this? A better question I'll ask you. If I had given you these four devices, can you arrange them in the ratio, in the order of resistance from the biggest to smallest? Suppose you have four devices, Esa, an ammeter of 10 ampere, ammeter of 5 ampere, voltmeter 5, and voltmeter 10. Can you arrange these four in the descending order of resistance? I am changing the question. Arrange these four devices in order of resistance. That would be a better question. Hmm. Yeah. D, B, C. Yep. Yeah. Most of you did get it right. So again, the same logic there. So for voltmeters, larger the range, larger the resistance. But ammeters, it is different. For ammeters, you keep it in shunt. You want smaller resistances because remember, R shunt must be smaller. For ammeters, larger the range, smaller the resistance. So that means here, first of all, the voltmeters will have the largest resistance. Among those two, D has the larger voltage, so D is greater than B. That is the first thing. The voltmeters will have the biggest one. So among D and B, D is the bigger one. Between A and C, if you look at it, A has the bigger range, matlab it has a smaller resistance. So then it will come C and then it must be A. Is this making sense, everyone? Among ammeters, the one with the biggest range has the smallest resistance. So between A and C, A is the smallest. Between D and B, D is the biggest. And voltmeters are definitely greater than ammeters. So DBCA. That would be a much better question. They'll give you four devices like this and they'll ask you to arrange in ascending or descending order. Have a look at this. It's a pretty good one. Clear, everyone? Any doubts? Anyone not convinced, please ask. Ali, clear with this? Abhinav? Malika? Falaksh, got this? Perfect. Going ahead, next one. Neil, clear so far? Yeah. Let's get this. questions are easy on these things, right? They're not really, you don't have anything out of the world questions. So we have a millimeter of millimeter means nothing that only, galvanometer. 10 milliampere resistance 9 ohm is joined in a circuit. It gives full scale deflection for current when A and B are used as terminals. Try, you got a minute. So what is the catch here? Now see, tell me one thing. Does the external resistance or the shunt resistance know who is the internal resistance? So here, when you connect the terminals between A and B, this would be your R shunt, and Rg will become 9 plus 0.9. Agreed? Because the shunt resistance won't understand whether the resistance this 0.9 belongs to the galvanometer or it is something in series. Is that making sense? Suppose if I connect the circuit between A and C, then can you tell me what is R shunt and what is Rg? If you connect between A and C, then R shunt is what? This, na? 1. Rg would be 9. You're getting it? So depending on what terminals you're choosing, Rg and R shunt can change. So anyways, in our question, it is given A and C. So then it is done straightforward then. So capital I is Ig into 1 plus Rg by R shunt. So you want to measure millimeter fans 10 ampere. So that is 10 milliampere. 1 plus Rg is 9.9 and R shunt is 0.1. That is 100. So that is 0.1 ampere or 100 milliamperes.
So it's 1 ampere, no?
Yeah,
It's
1
10 into
ampere.
100.
Yeah. 1 ampere. My mistake. So 1 ampere. Easy. So that's what I'm saying. Don't blindly mug up, R shunt, Rg, matlab Rg is the resistance of galvanometer. This shunt doesn't know who is Rg. You're getting it? So here, shunt fields 9 ohms and 0.9 ohms is Rg. That is the thing here. So sometimes in the question they'll say like that, a galvanometer, an extra resistance is added in series. Now find the new range karke. So if you blindly mug up the formula without understanding why you got that, you will get stuck. Let's get this. What is F ka value? A galvanometer coil has 90 ohms. So that is Rg. Full scale deflection 10 milliamperes. That is Ig. 910 ohms is connected in series with the galvanometer to make an voltmeter. This is R large. If the least count of the voltmeter is 0.1, matlab the smallest you can measure is 0.1. So for the F question, voltmeter is Ig into R large plus Rg. So 10 milliampere, 0.01. R large is 910 plus Rg is 90. So you can measure 10 volts. So now you're saying the smallest you can measure is 0.1 volt and you can measure up to 10 volts. So number of divisions would be 10 volt by 0.1 volt, 100 divisions. Make sense? That is the meaning of least count, the smallest measurement you can make. Let's get G also. Try. Others give it a try. Most, I think, yeah, some of you did get it, but others try. I'll give you a minute. This is the level of questions in mains or bits. That's where it said advanced. Mostly it is a potentiometer, and I don't know why the hell they removed it in mains portion. Advanced may we will not know until November. So let's see. So here the idea is, look at this thing. The ammeter is showing 0.1 ampere. Fair enough. The voltmeter is showing 12 volts. Great. And voltmeter ka resistance is 10,000. That is fine. Ammeter reading is 0.1 amp. What you want to find? So yeah. So and resistance of the ammeter is 20 ohms. Perfect. So you're done. Basically, the voltage across this must be equal to 12 volts. So I into R plus I into 20 ohms must be equal to 12 volts, isn't it? Because the voltmeter is in parallel, the voltage across this entire branch also must be 12 volts. And I is given as 0.1. So 0.1 R plus 2 is 12 and R is 100. Plus itna tha. Is that making sense? You know the current in the upper branch, you know the voltage across the whole branch. So then current into resistance of the upper branch should be 12 volts. Keep it simple. Like, entire instruments, right? It is simply series, parallel circuits and Wheatstone bridge. That's it. There is no big complex circuits. Kuch nahi hai. As long as you understand from the fundamentals, right? Circuit, the instruments will be able to handle easily. Clear? Any doubts on FNG, please ask. There, I'm keeping all these questions at one place only. Let's get them. Yeah. Try the both. Try both. This is same thing as the last one. An ammeter should have small resistance. True. Voltmeter should have large resistance. True. But yeah, okay, that was easy. What about this guy? This is a good one. Now you brought a non-ideal ones. Matlab they themselves have some resistance. So if you look at this circuit here, when you kept the ammeter like this, the resistance and the voltmeter here. Now see what happens. When you apply the Ohm's law, V is equal to IR, that I is the current in the resistor. So this is I in the resistor, this is the I in the voltmeter. So this thing is actually measuring IR plus IV. You're getting it? You're not measuring the actual current, you're measuring more than the actual current. So you're measuring IR plus IV is 4 amperes. The voltage is right because you're across parallel, this is 20 volts. So resistance R will be V by IR, which is 20 by 4 minus IV. So this value is greater than 5 ohms. Is that making sense? Because the voltmeter is not ideal, it takes some current. So the ammeter is not measuring the current in the resistor, it is actually measuring more than the current in the resistor. So the current in the resistor is actually less than 4 amperes, so the resistance is actually greater than 5. Same thing, I could have manipulated the question like this also, other way around. We have a resistance, ammeter. This time you get the voltage like this. I change the question here. Now in this case, it will measure the correct current, but now it will measure VA plus VR. You're getting it? And this thing comes out to be 20 volts. So now the resistance will be 20 minus V ampere by 4 ampere. This will be less than 5 ohms. This is the problem when you use ammeter and voltmeter to find resistance, because the ammeter and voltmeter always have some kind of an error, resistances. If you try to measure resistance using this technique, you'll always get wrong answers. So if you want to measure resistance, we have to find a better instrument. This is a bad idea. Using an voltmeter and ammeter to measure V by I to get R is a bad idea. That's where our second instrument comes, meter bridge. Is this clear, everyone? I is a pretty good question. Any doubts on I, please ask me. Clear, na, Neil? Clear with this? Arjun, Aditya, Abhinav, clear?
Yes, sir.
Yasha, Udian, clear? Saina, clear? Utsa, going ahead. Next thing is meter bridge. So meter bridge, right? It is to measure resistance. Again, like I said, these concepts are pretty straightforward. To measure resistance using principle of Wheatstone bridge. So this is how it looks. We have some metal frames like this. We have a wire like this. Here I'm showing a straight wire, but if you see the actual equipment, right, it'll have wires like this. So that you can keep more wires, you can keep more length of the wire. So even though it's a meter bridge, you will take it to be length L. So here you are connecting a galvanometer. with a jockey. So this needle kind of thing is called a jockey. So this black thing here is a potentiometer wire. It's a wire with uniform resistance. R naught and length L. Meta bridge mein you take 1 meter. So here you take a known resistance X, known resistance R, and unknown resistance X. So we need to find the unknown resistance. So we have a battery connected here. So the idea here is we'll keep moving the jockey. So initially, first you put it at something random, the needle will deflect in one direction. Then you keep moving this thing till you get the needle to get a zero deflection. The experiment is pretty straightforward. We keep moving the jockey till the current in the galvanometer is zero. Let's say this occurs when the length of the thing is x. काम करते हैं, x now will get confusing. Let's write it as Rx. So at this instant, the current in the galvanometer is zero. So when this happens, right, we say the bridge is balanced. So sometimes you'll hear this word, the bridge is balanced at 23 centimeters. So using this, we need to find that capital Rx now. Have a look at the experiment first. Like I said, the idea is pretty straightforward. Clear? Then I'll just read out the circuit in a simple form. So what you have is a resistor. We have a wire here. We have a galvanometer balanced here. This is Rx. This is R. This length is X. So this resistance will be R naught by L into X. This is L minus X. So this resistance is R naught by L into L minus X. And you're telling me the bridge's balance of current is zero. Is this a Wheatstone bridge? If the current in the middle resistor is zero, that means this by this should be equal to this by this. So when the bridge is balanced, this is a Wheatstone bridge. Or else the current won't be zero there. So Rx by R naught by L into X is equal to R by R naught by L into L minus X. So the unknown resistance Rx will be R into X by L minus X. There. Don't remember the formula, understand what we did. So you can measure the length X from an instrument there. We have a scale there. And once you know the length X, you are done. Substitute, you'll get the value. So you need a known resistance and you need the length. The advantage of this thing is, even though galvanometer has resistance, what is the current in the galvanometer? Zero. So there is no chance of getting an error only. The problem we had in an ammeter and voltmeter is they had some resistances. They're not ideal. That created an issue. Here, galvanometer has resistance, so the current is zero. So this gives a better result than using voltmeter and ammeter. But this also has its own problems. So there are certain precautions you have to take while using this. Let's see what are those. But as such, the concept is pretty straightforward. Any doubts on the idea here? Please ask me. So here there is one thing they'll ask you what happens. Few questions they can ask you. So the reading, right, resistance, the reading or the resistance is independent of area of cross section of the wire, because it will cancel out anyway, because what you want is resistance per unit length. So examine the last question like this: if the radius of the wire has become 2r, or the wire thickness is increased, how does it change? Will the reading change? It doesn't get affected. Resistance, or let's say x, actually balancing length, is independent of area of cross section. Means you use a thick wire or a thin wire, this is the same thing. Second, if the length of the wire used is large, if length of the wire is large, the value is more sensitive. You'll get more decimals. How do we use the word? We get more. You can measure the voltage more precisely. Actually, we get a more precise value. What do we call that? We get more accurate value. Yeah, we get more accuracy. Accuracy, nahi hai. We should say more precision. We get more decimals actually. If I just use 1 meter wire and if I got a resistance of 10, if I actually use 10 meter wire, I'll get something like 10.0. Means you can be sure it is more accurate. Because the jockey ka kuch thickness hota hai na, that is not accuracy, that is precision. We get more precise value. Accuracy and precision are different. There's a meaning, just to give an example, let's say the actual value is 4.713. Let's say this is the actual value. If someone gives me 1.342, this is a precise value, but inaccurate. But if you give me something like 4.7, this is accurate but not precise. So at least for 11th and 12th, precision implies up to what decimal you're pretty sure about accuracy, up to precision. The number of decimals. Accuracy is how close you are to the actual value. It's like this, I tell you, tomorrow there will be an earthquake at 11 o'clock in the morning, 11 o'clock, 13 minutes, 23 seconds. See, I'm so precise, but completely inaccurate. By chance, I don't know, but but if I say the earthquake can come anytime in the next 20 years, now I'm not being, precise. I'm giving you a very big range. This is a theoretical question, right? If the length of the wire is increased, what happens? You get more decimals actually. That is more decimals. I think better I read an example. Let's say length is 1 meter. Let's say we got R is 2.2 ohms. If length is 10 meters, then let's say we will get more precision. Let's say 2.01 ohm, something of that sort. You get more precision. So that is something. Now, there are certain precautions you have to take while using this. The first precaution is an end corrections. So when you're tying that wire, you don't exactly just tie there. You need some length. Since some length of the wire is used to connect it, we get errors. We need to include them. Meaning, let's say we have this. So when you connect it here, right, there's some wire here. So they will mention like this, the right end correction is 2 centimeters. They will mention like this. left end correction is 1 centimeter. So now when you get this reading as x and L minus x, in reality, it is not x actually, it is x plus 1. So the value becomes like r by rx by r naught by L into x plus 1. This is r by r naught by L into L minus x plus 2. So the length of the wire is not L, it is actually L plus 3. Clear? These are called end corrections. So in the question, if they mention, you have to include them. So this is one thing you have to be careful. Second thing, the jockey must not be dragged on the wire. So when you're moving it, you should lift it and put it at different places. Because if you drag on the wire, there's a chance the wire ka thickness will change. The wire will become non-uniform resistance. Once or twice is fine, but if you keep doing it over a span of few months, the way more you drag, the wire becomes thin. Jockey must not be dragged on the wire. So whenever you want to change it, you have to lift it and put it at different places. The second one is fine. First is also good. The third is the most important point. Any doubts on these two? The third one, you should definitely put a star for this. They did ask the questions on this. So when you measure this, you'll always get an error. The bridge must be balanced. In the middle 1/3 of the wire. What do you mean by that? Now, again, the same thing. So from here, we get Rx will be R into X by L minus X. So when you find the error here, delta Rx by Rx, R is the known value, so that is constant. We'll get error delta X by X plus delta L minus X by L minus X. Now look at this thing. So while getting the errors here, so the delta L minus X will be delta X by X plus delta X by L minus X. Now see what happens. If you try to measure, if this thing is balanced pretty close to this, what will happen? X will become very small. So this value will blow off. Suppose you balance more to the right corner, then what will happen? L minus X will become very small. So this value will increase. You're getting it? By chance, if the circuit is getting balanced on the edge of the circuits, right? If either X is small or L minus X is small, you get a big error. Getting it? So here, if X or L minus X is small, then error is high. And you can do maximum minimum, and you can prove that when L minus X is equal to X, that is at X is equal to L by 2, we get minimum error. That itself is a question. In a meter bridge, at what position it should be balanced to get minimum error? Exactly at the center. So when you measure exactly at the center, you get minimum error. But every time it is not possible to get in the middle. So what people said, at least middle 1/3 mein balance karo. Meaning you're talking from 33 to 63, 66 centimeters ka beech mein. So we should balance. So in the middle 1/3, the error is less. So if you use the left 1/3 or the right 1/3, if it by chance it gets balanced, then you should supposed to change this Rka value, the unknown resistance, and keep doing the experiment till it comes in the middle. So this thing has more to do with errors. Have a look at this. So that was asked in the exam. So in a meter bridge, it should be balanced in what options were: left one third, middle one third, right one third. Fourth option was it doesn't matter. Anything is same. Answer was middle one third. Meaning in the idealistic scenario, it shouldn't have mattered, but we always have errors. And exactly at 50%, the middle of the wire, the error is minimum. So that was another question. These kind of things will be advanced for more than one choice questions where they'll put, these statements in one of the options. But these are proper mains level questions. Even in advance, they can ask you. Like I said, the experiments are quite easy. The precautions and all that small fine data points, right? You should be very clear. All clear with this? Take a break, come back by 7 2. We'll continue from here. Any doubt so far? Okay, come back in 10 minutes. Yeah, Cam's on everyone. Let's start off. There, get this one. Easy questions. Like I said, there's really not much you can change. But let's do something weird in the next one. What is the answer? Independent of x. This is what I wrote, remember? When you increase the thickness, nothing changes there. The ratio of the distance will still remain same, no? You're getting it. So what you're indirectly doing is when you double the cross section of the wire, so this is what is happening. See, for A and B, the resistance will be, let's say, R. When the wire becomes thicker, double the diameter, we know R is equal to rho L by area, which is pi R square. So resistance will become R by 4. But you're not interested in that. What you're end of the day interested is a ratio, isn't it? The ratio won't change. So if this point is C and this point is C, RAC by RCB does not change. The overall resistance will change, but the ratio won't change. So the reading won't change. Clear? Next thing. Let's say we used a wire. Let's say this is 2 ohms, and let's say this is 4 ohms. Galvanometer is there. This is x is equal to 0, and this is x is equal to L. This resistance of the wire is not uniform. It is R naught into 1 plus x by L. Instead of using a uniform wire, we used a non-uniform wire. This x is the balancing length. So the bridge is balanced here and when x is equal to something. So find x when bridge is balanced. Just get the equation. So when x is 0, resistance is R naught, and when you go to L, resistance becomes 2 R naught. So it's linearly increasing. So the concept is same. Try, you got a minute or two.
I think you have to give the resistivity, no? R देके तो it is not making any sense.
Hmm.
I didn't get anything. How do I integrate it? तो
Welcome to
dr
life.
क्या होगा?
This is the resistance of the wire at a point X. Is that what you're asking? So this thing, okay, I got your point. Let's say this is not resistance, this is resistance per unit length. Happy?
Happy.
That's what you're asking. I got your point. You're not wrong. So resistance at a distance X for a small segment dx is this into dx करना पड़ेगा. Now आएगा भी. Let's see. The idea here is the end of the day it's a Wheatstone bridge. All that resistance and all is just to scare you. So basically, if I call this thing R1 and if I call this R2, since it's a Wheatstone bridge, so we should get the ratio 2/4 must be in the ratio of R1/R2. So R1 is nothing but R0 into 1 plus x by L into dx. Limits will go from x0 to x. R2 will be integral R0 1 plus x by L. Limits will go from x to L. Make sense? Isn't it? So all this resistance and all this resistance, the ratio should be 2:4. R0 will cancel. You'll end up with x plus x square by 12 by, this would be x plus x square by 12. Limits will go from x to L. This will go from 0 to x. This ratio is half. Are you getting anything good here? This thing looks bad, I guess. I don't know. That will be 2x plus x square by L is equal to L plus L by 2 minus. Yeah, I think you'll get something good. This will be 2 quadratic aega. X square by L plus 2x minus 3L by 4. You are getting x is equal to minus 2 plus root over 4 plus 4ac, so 3 by 2. We're getting x is equal to root 7 minus 2 by 2. You can check it out. It is solvable into L. Clear? I will leave it there. So the idea is that one. There's nothing there. That thing is just to scare you. End of the story is the ratio distance must be same. That's about the meta bridge. Now in meta bridge, there's another version of it. We call it post office box. this equipment, if you see, this is how it looks. That S shape you'll have. So the idea here is, so here you have this plugs.
Sir, is this a resistance box or a post office box?
This is actually a resistance box. We will create a post office box with this.
Oh, okay.
अगर post office वहाँ पे post office box नहीं है, let's see. So the idea here is this plugs which are there, right? Look at the terminals here. So here we can keep the terminals here. You can see this thing. You can connect them here. So these plugs, right? What happens? You can close them basically. You can close these plugs. So when you push them and pull them out, right? So this is what we get. For example, whenever by opening or closing this thing, we can add the resistance. I think we have to push them here. Or you have to pull them or something like that. But okay. So by pushing this plug, we can add resistance to the branch. So basically, this is a device, where you can change the resistances. For example, in this example, I pushed 400 and 3000. So I created a resistance between these two terminals is 4 plus 100 plus 3000. That is the meaning of it. So you have created a 3104 ohms. You're getting it? So by putting different plugs, I can create different resistance combinations. Clear with this thing? So instead of a jockey, right? This is another way of, instead of putting a jockey. I know that's a rheostat, but this is an old thing. Sabi, why do we call this post office box? Actually, because it was used in post office. Now, right now, right? Post office means it looks pretty silly now. But if you go back around 150 years, 100 years back, post offices, right, were centers of innovation. They're like the technologically most advanced places in the city. Reason, just imagine, you want to talk to someone. Especially, right, military used to have post offices completely under their control. It is not for civilian purposes. Because in a warfare, right, the most important thing is sending information. Getting it? So what we used to do, these people, right, we used to have this, post offices connected by these wires. They used to use simple Morse code. So Morse code, how it works, it's like, see, you have some kind of a key here. Basically, you're connecting a voltage here. So when you press this, as long as it is touching, you'll get like key. It just, the signal goes on. You're passing the current, isn't it? So that thing rings. So this is how you send a Morse code. If you just push it once and leave it, you get key. You're getting it long key and small key, long key and a short key. So basically, you created a binary code, zeros and ones. Getting it? So I don't remember the binary exactly, but let me see what it is. The binary code, right, is like, for example, say if you want to send A, so I'll send like this key. So I'll send a big one in the last. So this is understood. I sent an A. And this is one of the most respectable job, right? Meaning you are being a binary code transmitter or a binary code receiver on the other side. So just imagine at a distance of 50 kilometers, two people are talking using binary code. Suppose if you want to send, my name, so this is A. If you want to send R, it is like key. So it is like this. So the big one is a 1 and the small ones are zeros. So this is how the operators used to talk between the two post offices. So you want to send a message, right? Tomorrow attack at 11 a.m. with 1,000 soldiers. So you send all this information using binary code. And information matters a lot. Getting it? Let's say there is a castle or something and you want to attack from front and back at the same time. How will the other army know? Getting it? This is how actually Britishers used to control the whole thing. Think about it. They used to have like 4 or 5 cities Each city may they used to have a soldiers of 5,000, and you got an information that a crowd of 20,000 is coming and attacking this city. This thing used to send distress call signal to all these things, and they used to send support soldiers like 2,000, 2,000, 2,000, and they themselves have 10,000. They used to amass the army there and used to fight back. That is how you can control information. That is the reason whenever there's a riot or something, right, the first thing you do is cut off the internet. You don't let people talk to each other. Because once you have internet and WhatsApp, everyone will start sending messages and everything. Yaar, yahan pe ye ho raha hai, wahi pe ye ho raha hai. Just cut off all the communication. Don't let people talk to each other. Generally, whatever is the crowd or anything that dies down automatically in a day. When people don't have information, they just sit there at one place and they get confused. Right? Simple thing, na? Socho na. Let's say there's a riot going on in Ghatkopar. All you need to do is send 4 photographs of someone got killed and people get pissed off everywhere. Now you get pissed off, you start burning everything in Thane now. Fight hua Ghatkopar mein, by fight start hua Thane mein. Because the messages are spreading so rapidly, people get pissed off. So the best thing to do is cut off the internet. Don't let people talk to each other. They do signal jamming, stop everything. That's the first thing you do. You stop the communication. So the idea was this. So post offices, right, where itna kyun, even in 1980s, right, or 90s mein, if you want to send a message, it was very expensive. I don't think you have seen any movie. If you see old movies now, the hero gets a message. Father serious, start immediately. Kabhi suna aisa dialogue? So old movies, 1980s mein and all. Because that time, right, we used to call it trunk call. Let's say you want to send a message from Mumbai to Delhi, it's very expensive. So the bigger the message, more costly it is. So you need to send a message, but you can't send, hi, how are you, what are you doing, all fine. Ye sab bullshit hai. So keep the message simple and short. Father serious, start immediately. Bas ho gaya. That guy understood, I have to go home. So based on how many letters you send, you get it cost that much. Okay, so post office are used to connect like this 50 kilometer, 100 kilometers ka far mein, you can talk to each other using binary code. Instantaneous transmission, isn't it? So that time phones and all. And now the problem they faced is, let's say something happened, there is a rain or something, and the wire got cut off. Now, how do I know which post office should go and repair it? You're getting the problem is, I know I want to go and repair it. Let's say this is 80 kilometers and this is 20 kilometers. Now you and I know B has to go and repair it, but how will A and B know that they have to go and repair it? You getting the point? Which post office should go and repair it? So this is what they do then. So let's say if this is 80 kilometers and this is 20 kilometers, now A and B themselves don't know. So they bring this post office box. So I'll draw the simple circuit here. So this is one wire, and they will connect this to the wire which is disconnected here. They'll keep one more resistance here, one more resistance here. Then they'll ground this. They'll put battery here and then ground this. So here the concept is, we will assume this part is touching the ground. That is the thing we have to assume. And now see the circuit here. This is R1, this is R2, this is R3. This is your unknown resistance, the wire which is hanging outside. And here you have a galvanometer connected like this. Now using this meter bridge, R1, R2, R3 values can be adjusted. The R1, R2, 3 are adjusted. Till Ig becomes 0. So you'll balance the bridge. Then from here we can find R1 by R2 is equal to Rx by R3. From here I found Rx ka value. But I know Rx is nothing but rho L by area. I know the resistivity of the copper wire. I know the area of cross section of the copper wire. From here I can find the length. So when post office A does this experiment, let's say they get a value of something like 78 kilometers. When B does the experiment, let's say they got something like 19 kilometers with some error. Now roughly they have an idea, right? The distance between A and B is 100 kilometers. I'm getting 19. Matlab it is closer to me, so B should go and repair it. Are you getting the concept behind it? So the wire which got broken, we will treat that as an unknown resistance. So this thing, so wire is broken, fallen on the ground. So that was the idea. It has to fall on the ground. If it touches some tree or something, it might not work that good. But at least immediately, right, these people will set out with a team and go and get it repaired. Because like I said, communication is quite important. Idea is clear? So we call it post office box because it is actually used in post office like that. So idea was that. Then I think about this. Do you remember I told you this thing? Hannah, why there's no guarantee it'll touch the ground. So, but better than nothing, right? Kuch to hai at least. So, did I tell you about the dog, which can detect phone calls? I didn't tell you a dog which in Britain, right? I think it happened like few years, not few years, matlab, it's an old story. Actually happened. So there's an old lady, right, which went to the telephone company and complained like, I'm scared of my dog. Whenever I get a phone call, my dog knows the phone call comes. And the telephone company were looking at this old lady like, ye to kuch pagal ho gaya types. So like, how will the dog know there is a phone call? But not to offend the old lady because senior citizen and all, they said, okay, ma'am, we will send someone to check it out. So a person went to the house. He was sitting there and the dog started barking. And then the phone call comes. Then he thought, okay, maybe hota hai kabhi kabhi coincidentally. So then he waited for some more time and someone else called the call. Again, dog started barking and the phone call came. So every time before the phone call, the dog barks just before like few seconds, 10, 15 seconds before the dog barks, and then you get a phone call. That means somehow the dog knows there is a phone call. So this guy went out to do an inquiry. He started searching everywhere. And what he found was the telephone cable. If you see a telephone cable, a landline, it actually has a low voltage wire. It's a 50-volt wire. So that wire got cut. It fell down on the dog ka cage. Okay? And the other wire is here. So it got disconnected. So whenever someone is calling the house, the dog is getting an electric shock. In that process, it is barking and howling. And in this process, it is urinating. And that urine is going and touching this part of the wire. And urine is a conductor. So circuit gets connected and the phone rings. So that is how the dog knows there is a phone call every time. So the poor dog is getting electric shocks every day, right? And you thought like dog has some superpowers. Unfortunately, that is the sad part. So that is one thing. So things, right? Certain things you can't explain and all. So you should not get into superstitions. Maybe there is a reason which you don't know. Did I tell you about this? The car which does not like vanilla ice cream. So this is a Volkswagen car. I think in Europe or US. Again, 1980s time period. So there is a family, right? So this guy, right? In the family, every Saturdays they used to go and buy ice cream. Abhi to Swiggy sab aa gaya, but that time you have to go to a shop and buy ice cream. So Saturday was an ice cream night. So the dad used to take all the kids and go to the ice cream shop and Saturday and buy. So whenever he used to buy vanilla ice cream, the car doesn't start. You buy any other flavor, car starts. So initially he thought car ka kuch problem hai. But and every time when you buy vanilla ice cream, right, you have to tub it. And after a month or so, he realized that pattern. Whenever he buys vanilla ice cream, car doesn't start after that. And this guy literally tested. He used to go and buy vanilla, car doesn't start. You buy any other ice cream, it starts. Now this guy like got confused. Matlab, what is this? So then finally, right, he decided to write a mail to the company. So he started the letter something like, my name is so and so. This is my credential. I work in a big company. Blah blah blah. Please don't think I'm mad. Getting it? Getting it obviously ready. If you're going to say my car doesn't like vanilla ice cream, people are going to think you're mad. So he writes a letter like, see, this is what happens every Saturday I go, and whenever I buy vanilla ice cream, for some reason the car doesn't start. But if I buy any other flavor, it starts. I know it looks completely weird, but it is true. Please trust me. Something like that. He writes it in a very polite tone. And then the company engineers actually read the letter and they said, okay, this guy might be bad or there might be some problem with our car. So let's assume it is our problem. Let's send someone. So they send an engineer. He goes to the house. So the engineer sits beside him and they said, okay, let's go. They both go to the shop. They buy vanilla ice cream. The car doesn't start. That guy says, perfect. What you said matches. So please give the car back to us. And they gave him a new car and said, you use this. We will find out what is the fault. So this guy takes the car. So now see, this is what I was saying. When you see something which you can't explain with what you have, you need to do more observations and try to figure out rather coming to a conclusion. This thing, right? We suddenly come with the conclusion, yaar, car ko ice cream acha nahi lag raha hai. Next day, the newspaper mein aa jayega, it will become pretty famous. So this guy, what he did, he took the car, so he made a table. So he went to buy vanilla ice cream, then he went to buy chocolate, then he went to buy everything. He literally brought every ice cream and he recorded the times. He did this multiple times. And every time they brought vanilla, it didn't start. It was clear it was not starting when he buys vanilla. Then what he observed was whenever they order vanilla ice cream, the order comes less than 30 seconds. But every other flavor takes more than 60 to 90 seconds. This is the first observation he got from the data. And then the point he realized is vanilla is the most ordered ice cream. So what these people did near the shop, they kept a big container here. They kept vanilla boxes here only. So when someone orders vanilla, you just go take it and give it. But if you order any other flavor, the person has to go to the back of the shop, get the box, come and give it. It takes around 60, 90 seconds. So in this process, what is happening? The car had a problem actually. The engine, right? When you come to the place and stop the car, the engine is still heated. Because of the heat of the engine, the fuel is in a vapor state. It's called vapor lock. The vapor is creating enough pressure not so that the fuel is not going into the engine. It is not getting injected into the engine room. But if you wait for a minute or 2 minutes, the engine cools down, the vapor goes off, and the fuel goes in. So there is a problem called vapor lock. Now, these people never thought you'll have an issue like that, but they realized. So they went there and they understood one thing: there's something problem with the timing. It's not the ice cream. So that means if you buy vanilla ice cream and just wait there for 1 minute and start, the car starts. So it was never the vanilla ice cream. There's a problem with the vapor lock. Then they went back, redesigned the engine, they recalled all the cars and repaired it and sent it back. That is the car which doesn't like the vanilla ice cream. So when you see something, maybe there's an explanation. Maybe right now you don't know. So be careful when you hear superstitious stories. So, anyways, coming back to this. So this is how to use this. This thing is mostly a good theoretical question. Right? They'll ask you like where to connect what. So we have this plugs here. So this is what we do. See, I am trying to create a Wheatstone bridge, right? So I need 4 resistors. I need to put a galvanometer and I need to put a battery. So let's first keep the terminal. So let's call this terminal A. Let's call this terminal B. Let's call this terminal C. And let's call this terminal D. So first thing, I need to connect the battery between A and D. So let's name this point. So let this point be D. D is the corner. I need to connect a B. So let this be B. Let this be A. And let this be C. I can pick any point. So you know what we're doing here? By closing this plugs in the middle. So by closing this plugs in the middle, you're changing the resistor between BD, isn't it? So this is what I was saying. So you can adjust the values of R1, R2, R3, and R4 by adjusting the that jockeys there. So let's say R1, R2, R3, and let's say between C and D, you're connecting the unknown resistance. So you're connecting that unknown resistance between this. So this is what you have to find. So basically you want to create 3 resistors. So you create one resistor here between B and D, you created R2. So this junction is R2. Between A and B, you create R1. So by closing this flux, you can change R1 ka value. So this is R1, this is R2, and this is R3. So we keep R3 the biggest one. Nothing special. You can keep anything as bigger. So now you're getting, by changing the plugs, I can change R1, I can change R2, I can change R3. Is that clear, everyone? And where do you keep the galvanometer? Between B and C. So I will keep the galvanometer between B and C. And where is the battery? Between A and D. There. So this S shape becomes a circuit like this. So R1 by R3 is R2 by Rx. So instead of potentiometer wire or a rheostat, this is the thing which we used to use before. It is easy to just, push the plugs. So by adjusting R1, R2, R3, we can balance the bridge. So exam they'll ask you like this only: between which two terminals is the battery connected? Between which two terminals the unknown resistance is connected? Between which two terminals the galvanometer is connected? So that is the kind of theoretical questions you'll get. And in this thing, you can always, interchange battery and galvanometer, still the answer works. Means you can connect the battery between B and C and galvanometer between A and D, it still works. Battery and galvanometer can be interchanged. That was a question they asked in the exam. A galvanometer and battery can be connected between which 2 points? There were 2 options. It was like between BC or AD. So in this especially, you'll get theoretical questions as such. There's nothing big on this. So this is another variation of meter bridge. People didn't want to deal with wires and all. It is not a pretty sturdy one. This thing, if you look at a box, right, it looks pretty sturdy. The post office box, meaning this is completely made of metal, right? So there's no chance of breaking, wire becoming that and all nonsense. Kuch nahi hai. The resistances are hidden inside. So it is pretty safe. You'll get some errors, but it is fine. Clear with this? That's about the meter bridge and the post office box. So post office box is nothing but a variation of meter bridge. Clear with this? The next thing, potentiometer. Now, again, potentiometer is easy if you know the circuit well. So understand the circuit and how it works. Idea is pretty straightforward. We will finish all the theory today. Next class, we'll do more problems on it. But like I said, it's not there in mains. Advanced main is still there. So potentiometer, it is used to measure unknown EMF and internal resistance. So if you give me a battery with, I don't know, I need to find its EMF and resistance. So this is the thing which we use. So ammeter measures current, voltmeter measures voltage, meter bridge measures resistance. This thing measures EMF of a battery and internal resistance of a battery. So first thing, how does the circuit look like? You should mug up this circuit literally. Literally every time someone says potentiometer, if you can draw this, it will become a little easy for you to understand what is happening. So we have, this is E primary. This is R primary. This is your unknown resistance EX. This is your unknown internal resistance RX. This is an R known resistance. That's your galvanometer. This is A and this is B, and this is a potentiometer wire. The resistance is R naught. Length is L. So this lower part is the secondary circuit with a switch. The upper part is a primary circuit. The jockey will move on the wire AB. So in this circuit, we know EP, RP, R naught, RK, L. We know all these values. We need to find EX and RX. Like I said, it's pretty simple concept there. So let's see how this works. First, have the look at the circuit. Sometimes that wire will be pretty big. Like I said, if you have a long wire, it will be more sensitive. You'll get more decimals. So for simplicity, I'm just putting one wire for you to understand. Clear? Now let's see how it works. So first thing, to find the EMF, what we do, keep the switch open. Now let's draw the circuit again. That's what I'm saying. Just understand what is there. Don't try to mug up the formulas here. We can mug up one or two. I'll show you, but let's see what is the process. There. This is how the circuit looks. The lower one is disconnected. The lower one is just hanging in air, so that is useless anyway. Now you're saying the bridge is balanced, Ig is 0. Now look at the idea here. It is straightforward. Let this length be x. Let this point be A. Let this point be C. This is B. Now if this is A, this let's call it A dash. So whatever current flows in this circuit, all this current will go in this branch only. Agreed? Where I is equal to EP by RP plus R0. Now in this branch, Ig is 0 because the bridge is balanced. If that current is 0, this current is also 0. Do you agree? Because the current has to come from here only. There's no way out. Is that clear, everyone? So now here the idea is this. This point is potential C dash. Now you can clearly see here, VAC must be equal to VA dash C dash. Do you agree with that statement? Because A and A dash are the same potential. C and C dash must be same potential because current is 0. A and A dash are same. C and C dash are same since Ig is 0. That's it. This is the main concept in this thing. When the bridge is balanced, the potential difference across this wire must be equal to potential difference across this circuit. Are you getting that? Then, so in this branch, the current is 0. Perfect. So what is VAC? So VAC is VA dash C dash. So VAC will be current I into resistance across AC. VA dash C dash is nothing but EX minus I into RG. Right? But this term is anyway 0. There is no current in that. So I will be EP by RP plus R0. RAC is R0 by L into X is equal to EX. Done. There you are the EMF. EP is constant, R0 is constant, RP is constant, R0 is constant into X. So this is proportional to X. Is the idea clear, everyone? So to find the EMF, what we do, step 1, keep the switch open. So bottom ka, this thing is useless. Then keep moving till the bridge is balanced. When the bridge is balanced, the current in the galvanometer is 0. So this current Ig is 0. If Ig is 0, then this current entering the unknown battery is also 0. So current only flows in the upper primary circuit, which is given by EP by RP plus R0. Now this point A and this A dash both are connected by wire, so they have same potential. Point C and C dash must be same potential because current is 0. That means A and A dash ka potential is same, C and C dash ka potential is same. So therefore VAC must be equal to VA dash C dash. Hope that is clear. So AC ka voltage is current into RAC. This is EX minus IRG, but I is 0. Because it is balanced, so this current is 0, that is 1. So if I know all the remaining values, I can find the EMF of a battery. So Ex is proportional to X. But while doing the experiment, people really don't like this because you have to calculate EP, R0, RP, R0L. It is too much of an headache. So what they do, alternate. First have a look at this process. Idea was clear. If you ask me in the potentiometer, what is the concept? This is the concept. AC is equal to A dash C dash. That's it. That is the only concept. You'll get everything. You should know how to know the circuit and you should know that potential difference will be same. So this is what they do. In the lab, right, when we do the experiment, we use two batteries. EMF, let's say E1 and E2 in same polarity and reverse polarity. We do the circuit 2 times. Same polarity. And we repeat the experiment. When they're in same polarity and reverse polarity. This itself is a question in the exam, right? So the circuit looks like this. So in the first case, both the batteries are like this. Given E2, and let's say the bridge is balanced at L1. Now I don't know EP, GP, nothing. I don't know all those values. Second case. So in that E1 or E2, right, we take one unknown battery and one known battery. So second case we'll put like this and like this. Now it will be balanced by L2. So just now we saw, so when they're both in the same direction, so we get E1 plus E2 should be proportional to L1. Here E1 minus E2 must be proportional to L2. Because it is the same setup, the constant will remain same. So we can get from here E1 by E2 by E1 minus E2 is equal to L1 by L2. So among E1 and E2, if you know one of them and if you don't know one of them, if anyone is unknown, you can find the answers. So from here you can find E1 and E2. Clear with this? So from here you get E1 by E2 ratio. If E1 is unknown and E2 is known, you'll get the unknown ka value. This is a much better method. Reason, even if you add some error, the error will cancel off in that ratio. So you need not find this constant ka value. That will be taken care when you use two batteries. That is the good thing about this method using two batteries. Here L1, L2 are the balancing lengths. Is this clear, everyone? Next thing, how do you find Rx? Any doubts, please ask me. I hope the method was clear. This was a better method because you don't want to find that constant. You take one battery unknown, one known, put them in polarity, you'll get some length. Put the reverse polarity some length, to get the ratio, you'll get the answer. This is what they use in the labs. No one actually measures the TP and all that. Clear, no? Next thing, we need to find Rx. Now what we do, close the switch. So you already found Ex from the previous experiment. Now the problem is, if the current doesn't flow in the battery, how will you get Rx ka value? So this is EP, this is RP, this is R naught, this is EX. EX ka value I already know, and this is R known. So here the current I will flow like this. All the current will go in this only. When the bridge is balanced, current in the galvanometer is 0. So this current is also 0. This battery will produce its own current I, and that will flow in its own branch. So basically both the circuits will behave independent of each other. Let this point be A, let this point be C. Let this point be A dash, let this point be C dash. Idea is still the same. A and A dash are same, C and C dash are same. Why? Current is not there in the galvanometer. So capital I is EP by RP plus R naught. Small I is EX by Rx by R known. And voltage across AC must be equal to voltage across A dash C dash. Like I said, that is the main concept, that AC ka voltage and A dash C dash ka voltage is equal. So AC is nothing but I into RAC. A dash C dash is nothing but I into RKX. RK. I can do EX minus RKX, but I into RK is also good. So this is E primary by R primary plus R naught. I know everything. RAC is R naught by length into X. That's the balancing length. I will be EX by Rx plus RK into RK. There. If you see, I know everything except Rx. So shift everything there. You can find from here. You'll get Rx is equal to something. Is the concept clear? That's it. So like I said, this is the main concept. So when you close the switch, you have two independent circuits. Current is flowing in them independent of each other. Find the currents, find the voltage across AC, find the voltage across RK. Both the voltages should be same. So when you equate them, here you know everything except Rx. So you'll get Rx from there. So open the switch, you'll get EMF of the battery. Close the switch, you'll get the internal resistance of the battery. This is how you find both. Clear? Now, sometimes you can do it much faster without doing all that if I just know the balancing lengths. This is how they'll frame a question. This is how they'll mention. They will say when the switch is open, balancing length EX is proportional to L1. So L1 is the balancing length. When switch is closed, the EMF will be EX minus IRX is proportional to L2, or you can take I into R known also. L2 is the new balancing length when the switch is closed. And we know current I is nothing but EX by Rx plus R known. So if you put the ratio EX by EX minus IRX will be L1 by L2. So from here also you can calculate Rx. Same thing what we did, but everything in terms of balancing lengths. So exam they'll give a question like this. When the switch is closed, the balancing length is 40 centimeters. When the switch is opened, it is 60 centimeters. Find the unknown resistance. So if you know what you're doing exactly, meaning the balancing length is nothing but this voltage is proportional to the length. That is a game you're playing. Is this making sense, everyone? So please do go through this entire potentiometer experiment again. Getting it? So next class when we catch up, we will see this again once more, and then there are some precautions. That is the most important one. And then we'll do some problems. So next class, first half, we will finish off this. And then we'll start off with magnetic force. So most of the chapter is done. Like I said, potentiometer is only there for advanced part. That is also not confirmed till the portion comes, but let's assume it is there. But quite an important one. Questions are good. They're not difficult. As long as you understand, you are just playing with only one thing. AC ka voltage is A dash, E dash ka voltage. That's it. That is the only game you're playing in potentiometer. You should just know the circuit, how it looks when you're closing the switch and when you're opening the switch, and you can play the game. So this is the theory part, but in the lab, this is what you do. This is the theory part for finding unknown resistance, but in the lab, this is what you do. In the labs, you always find the unknown balancing lens, and from there you try to find the values. Okay, so with that, we'll wrap up for that day. So make sure to go through this. We touched almost 40 questions, I guess. Yeah, we touched 40 questions. This ammeter and voltmeter is only 9 questions in there. So simple ones. So do make sure to resolve the entire notes and start doing current. If you have not started, or if you started doing, do finish it off. Keep a deadline, at least till next Friday, finish it off, whatever you're solving. Because this Friday we'll finish off current and we'll start off magnetism. Magnetism is again 3 small chapters, 3 chapters: magnetic force, magnetic effects of current, bar magnets. So there are 3 parts like that. They won't take much. I think any other 2.5 classes we finish off each one. The small ones, and then comes EMI, AC. Then we'll do wave optics and modern physics. So we should be done by before Diwali. We'll finish the advanced part. Chota semiconductors and all those, things which are there for only mains might be left out. That we can do later, because you guys won't remember anyway. That is like inorganic physics. Okay. So anyway, with that, we'll have a